So this is the Particles Homework Booklet question 36, and we're told that in experiments based on the photoelectric effect that they support the particle nature of light. In such experiments, light is directed at a metal surface, and we're asked to state what's meant by the threshold frequency. Need to just be careful here, it is asking us about frequency of the incident light, so we need to reflect that back in our answers really. So it's the idea that below a certain frequency no electrons are released, emitted, liberated, whatever your favourite word is there. Or if you wanted to put it another way, that if we're below that minimum frequency, again it's the idea of we have to be if we're below the frequency, and it's that minimum frequency for the electrons to overcome the work function. Then asked to explain why the photoelectric effect is not observed below the threshold frequency. And the key here is that electrons are being released by individual photons. This is where the particle model really does its thing over the wave model. We have to think about what's going on in terms of electrons, individual electrons being released by individual photons. That energy of that photon depends on its frequency. Again, referring back to the frequency there, and it would be quite useful to quote the equation E equals HF there, because that sets out that relationship. And below the threshold frequency, the photon does not have enough energy to liberate, release, emit an electron. So we've got some light of that wavelength, 5.4 times 10 to the minus 7 meters. That's incident on a metal surface, and the work function is that. And we're asked to calculate, first of all, the energy of a single photon of this light. We've got, if you like, a little bit of dummy information. We don't need this at that stage. I would probably jump straight in and use E equals hc upon lambda. I say that's what the mark scheme says. I think I probably would actually. I'll explain that in a moment. Again, picking up H from the formula booklet, picking up C from the formula booklet, and then lambda from the question goes straight in, and I end up with that value. In practice, actually, I don't know why I have a thing about that equation. I just love to remember C equals F lambda and E equals HF, so I'd probably have done it in 2 steps, got to the same place. From there then we're asked to calculate the maximum kinetic energy of an electron that's emitted from the surface. So we can use the basic equation for the photoelectric effect. HF is phi plus Ek max. The photon energy is the work function plus the maximum kinetic energy. From that I can work out that maximum kinetic energy, and remembering, if I just reorganize this, we've already worked out HF, the photon energy. That's the work function which was given to us in the question, and then simply do the maths and we end up with 2.28 times 10 to the minus 19 joules. From there, we're asked to calculate the maximum speed of the emitted electrons. What we can't do here, which some people try to do, was some stuff around C equals F lambda. Yes, particles have wave-like properties, but they're not waves. They don't follow the wave equations. So we can't use C equals F lambda, but we do have a maximum kinetic energy, and you maybe remember Ek equals a half mv squared from your GCSE. If not, we're coming back to that again soon. So I can rearrange that, and given a particular maximum kinetic energy which we'd worked out in the previous part, I can rearrange. So I multiply both sides by 2, divide both sides by m, and I end up with v squared is 2ek upon m, square root both sides, and I can calculate the speed I end up with, 7.08 times 10 to the 5 meters per second. And then finally, we're asked to calculate the de Broglie wavelength of the fastest electrons. Lambda is h upon mv, h from the formula booklet, m from the formula booklet, v that you've just calculated, and we can get to 1.03 times 10 to the minus 9 meters. So that's the Particles Homework Booklet question 36.